Interested? If you take this and you apply it to a material in Unity, and you put that material on an object, it will render in white. So you'll just have white. And I'll explain how it works bit by bit. So every shader lab file has one shader. That's the first line, and it describes a name. Okay, that name is how it appears in the Unity editor. So the Unity editor, when you select the shader, has got a little drop down that categorizes stuff, and the slash is for like a submenu. So this one would appear in the custom submenu, and it will be called basic. Okay, that's what the shader line does. Every shader lab file has one of those lines, and then it contains a whole bunch of other stuff. So what it contains is a subshader. Every shader lab file must have at least one subshader, but it can have multiple ones. So the surface shaders and perhaps other complicated stuff that you want to write will have multiple subshaders. Unity will pick the first subshader that is supported on the hardware that you're using. So you might want to write simpler versions of effects so that they can work on Shader Model 2 hardware, and more complicated ones that work on DirectX 11, amazing hardware with like whole shaders and all sorts of fancy things. And Unity will use the first one that it can. So the order in which your subshaders appear in your file is important. Then there are passes. So every subshader has a number of passes. It'll have at least one, but it can have any number of them. For every pass in a shader file, your object is rendered once. So if you have multiple passes, your object gets rendered more than one time. So for complicated effects, and in fact for how Unity handles its lighting, you will have multiple passes. You can also use them for complicated effects, like say you want to do a blur. Most blurs are two-pass effects, so that they can blur in one direction and use only a certain number of instructions, and then use that same blurred buffer in one direction, blur it again in the other direction, which is the same as blurring in two directions, but you use far fewer texture lookups this way, because you're blurring pixels that have already been blurred. It'll make sense. So the pass. The pass contains CG code, okay? And the CG code are contained within the CG program and NCG tags, okay? And they usually exist inside a pass, but you can also put them outside of a subshader inside of CG include blocks. So for those cases, those bits of code that are outside the subshader are included in all of your subshaders. So it's useful if you have common code, you want to put sort of functions that you reuse or variable definitions or whatever in a common sort of place. It's useful to put them inside CG include blocks. And then the code itself. Okay. So CG is a C-like language, so I should hope that you can all read that. But it has a couple of unique things that all shader languages have. Okay. So the first one is that include line. That include line works like any include in a C-like language, where it takes the context of that file and it just shoves it into your shader. So the CGInc file, this particular one, is one that is provided by Unity, and you can see its source code in your Unity installation folder under editor, data, CG includes, if you're interested. I mean, you can see everything that it has. So it includes a bunch of useful things, it includes a bunch of useful handy methods that you might use, and it includes that app database, right? So that is the input to our Vertex shader, and it's a structure that looks like that. Okay? You can code that yourself, and you can put it in your CG program, but it's far easier to use the one that Unity already has for you, because it's already there, so you don't have to bother. Generally, this doesn't change very often, but there are 3 different variants of this app data that you can use depending on how much information you need to take from your vertex buffer. So this one has the position of the vertex in object space, it has the normal of the face in object space, and it has texture coordinates for UV map. Okay, that's what this includes, and that's app database. And then that brings us to semantics. So semantics are those bits after the colon that you saw in those definitions. So there's something that's unique to shaders, and they tell the GPU what information it's working on and how the information from the vertex buffer maps to your arbitrarily named variables. So you can call the variables whatever you want, but the semantic tells the graphics card how to get it and what to do with it. Okay? It tells the graphics card also how the interpolator will handle the data. And the vertex shader will generally use semantics that look like this. So they're for vertex color, for normals, for the position in object space, for the tangent, which is kind of like a normal, but it's rotated, so it's along the face, and texture coordinates. Okay, all of these things you can have multiple versions of. So if your mesh or if your output to your pixel shader needs multiple versions of these, you can append them with a number. So you can have color 0, you can have color 1, you can go all the way up to, I think it goes up to 32 for each one in DirectX 10, but I could be wrong. Generally, you'll probably stop at 7, so you'll go from 0 to 7 and you have 8 of these. And that gives you the highest compatibility across various hardware. So the more you need, the higher shader model and the more advanced graphics card and the more advanced hardware that you need in order to support the shaders that require more inputs. And then the Vertex shader sends information to the pixel shader, or the fragment shader if you will. And it also uses semantics, but it's got fewer of them. So generally the only semantics you care about when sending stuff from your Vertex shader to your pixel shader are those two. It's a color and a texture coordinate. But you don't usually use, or you don't always use them to represent those things. Because again, those, the values that your graphics card are working with are entirely arbitrary. They can mean whatever you want. So you can pass information into a text code that describes the position of a light, or a color of a light, or where something is in world space, or whatever. So whatever you need, you would pass them through using those. They are different, however, in the sense that color on most hardware, but not all, clamps to a range of 0 to 1, because that's generally how you represent color. Texture coordinates do not clamp. So that's generally the important distinction between the two. Okay, so we get to this. It has a vertex shader. So what the vertex shader does is it takes an input, which is that structure that I described earlier, which has a world position. The world position is all we care about right now. And it outputs a 4-dimensional floating point value. Okay? The 4-dimensional floating point value is the output of the vertex shader that goes to the pixel shader, and it is the position of this vertex in clip space. So that is what I described that vertex shaders need to do. Above all else, the one thing that every vertex shader must output is this position, and the position is in clip space. And in order to do it, we do a multiplication. So there is that built-in function called mul. That is a matrix multiplication. Okay? And what we do is we take that Unity matrix MVP, which is a matrix that Unity provides to the GPU that describes the combined world matrix, view matrix, and projection matrix all in one. So you can take something from object space into projection space with just one multiplication. So that line is transforming your input vertex into clip space. That's all it does. One line. And then you return that value. And that's what a vertex shader needs to do. So the simplest vertex shader just returns a position in vertex space. And then a fragment shader returns a color. So the color is what color that pixel is going to be on your screen. So here we're just returning a sort of straight 1, 1, 1, 1. It's 4-dimensional because colors have red, green, blue, and an alpha channel. So that's why it's 4 dimensions. And the alpha channel is usually used to represent transparency. So if something is 1, it's completely opaque, and if it's 0, it's completely transparent, so it's invisible, and sort of in between numbers shade something lighter or darker. But that is where blend modes come in. So even if you had to change that in this particular shader, it wouldn't make a difference unless you have a blend mode, but I'll explain that in a little bit. So 1, 1, 1, 1 is white. So when you return that white, you're going to have a fragment shader that just returns white. So if you had to try this in Unity, and I do actually encourage that you do, and you put it on an object, you'll get a white cube. But that's not very exciting, right? So it helps understand the flow. By the way, is everyone still following? Does anyone have any questions? Now's a good time to ask questions. Half precision floating point value, so it's only 16 bits. It generally represents a range of roughly about 60,000, and you get about 3 digits of precision. What is true for all floating point values, though, and this is important, is they lose precision the further away they get from 0 because of how they're represented as exponential. So internally, GPUs and CPUs represent floating point values as a mantissa and an exponent, and then together they form your floating point value. And as a result of it being exponential, you get the most precision when a number is small, which is why most shader stuff, you want it to happen in a range close to 0. But the half precision exists for when you know you can fit it into half precision, and then you save bandwidth for your GPU. There's also fixed, which is a low precision value. It's usually 11 or 12 bits. That doesn't matter. But the difference between fixed and half is that fixed is not floating point. So fixed has fixed precision in its whole range, but its range only goes from -2 to +2. And their precision is roughly 1 over 256. So you can represent a color really well with fixed, because colors tend to move in 256 increments. However, what's important to note is that these data types aren't always implemented in GPUs. Most desktop GPUs actually just treat everything as a float. So they don't have half precision. Half precision just ends up being a float. They don't have fixed precision. Fixed precision just ends up being a float. But you can use the symbols anyway for hardware where it does matter. But the problem with doing that sometimes is that if you're testing your shader or whatever on a hardware that does this, and they won't usually tell you, so it's nothing you can know in advance, but you'll notice that some things look correct when run on a desktop GPU, but don't look correct when run on, say, an iPhone, because the iPhone actually has a fixed point structure in its GPU, and perhaps your shader was going over the 2 range, so it looks correct when it's represented as a float, but it doesn't look correct when it's represented as a float. So that's something to bear in mind. You can, strictly speaking, just use floats for everything, but while GPUs are amazing, they're not that amazing, so you generally want to make as many concessions in their favor as possible, that you can push as many pixels as you can and make something look amazing. So optimization is very important for GPUs, and using the lowest precision data type that you can is always a good idea. And then they have a cool sort of shorthand where you can just append a number to the base data types and turn it into a vector. So float 4 is a 4-dimensional float, and half 3 is the 3-dimensional half, and fixed 2 is a 2-dimensional fixed. And you can do that in a whole bunch of different ways. And you can do it for matrices as well. So when you represent a matrix in CG, you represent them like that. So float 4x4 is a 4x4 matrix, which is what all of those projection matrices that are built into that Unity MVP matrix is a float for 4x4. So it's a big table of numbers that handles the transformation. So when you want to represent matrices, and they don't have to be square, by the way, so you can have a 4x2 matrix, you can have a 3x1 matrix, whatever. Although a 3x1 matrix is just a float 3, so whatever. So that's how you represent those data types. So let's make that shader better, okay? Right now it's not very useful because it's just rendering stuff in white. But that white value that we pass into the fragment shader, we can make a parameter instead, so that you can set that color to whatever the hell you want. In order to do that, ShaderLab has this properties block. The properties block is everything that appears in your shader in Unity. I can show you. And they go right on top. So inside the ShaderLab block, but not inside the ShubShader block, this is the first thing you're going to have in your file. And you will add properties like color or textures or floating point values or whatever into your properties block like this. So adding this one to the properties block will give you that customizable color thing, okay? And the bit at the end is a default value, so it's going to default to 1 if you don't set it to anything else. And then you need to take this value and you need to read it in your shader, okay? So we have this color value, and Unity sets it and sends it to the GPU along with your material, and all that stuff happens for you, but your shader needs to work on this value. So in order to do that, you just have to declare a matching variable inside your CG program with the same name. So we declared an underscore color, and by the way, the underscore thing is a convention that you don't have to follow, but generally speaking, any properties that you pass in and any ones that are built into Unity use the underscore convention just so to be consistent. The particular thing with color and texture is if you call your color underscore color and you call your texture underscore main text, which we'll get to in a little bit, Unity's scripting interface has a few shortcut properties, and one of them on a material is dot color, and dot color maps to that. So if your color is not called underscore color, dot color won't change this particular property. So it's a good idea to call your main color underscore color for that reason mostly. So you declare a color, and we're making it fixed again because we know colors have a range from 0 to 1, and that's it. So fixed is fine. And we change our fragment shader to that. So the fragment shader, instead of returning a fixed value of 1, it returns the color we passed in, right? So it's pretty much exactly the same, except we're taking a parameter now. And in Unity, if we had